Preparing for a PySpark Developer interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question, you'll see a sample answer, followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. What is PySpark, and when would you choose it over plain Python or Pandas? PySpark is the Python API for Apache Spark, used to process large datasets across a cluster. I choose it when data is too big for one machine, or when jobs need distributed compute, fault tolerance, and integration with data lakes. Pandas is faster and simpler for small in-memory data, but PySpark scales better for terabytes. The key is not using PySpark blindly. Cluster overhead only pays off at scale. While answering, focus on distributed processing, Spark clusters, JVM execution, DataFrame APIs, lazy evaluation, fault tolerance, and when Pandas is still better for smaller in-memory datasets. Question 2. Explain the difference between RDD, DataFrame, and Dataset in Spark. RDD is Spark's low-level distributed collection API. It gives control but lacks schema and query optimization. DataFrame is a distributed table with named columns, schema, catalyst optimization, and efficient execution through Tungsten. Dataset adds compile-time type safety in Scala and Java, but PySpark mainly uses DataFrames because Python is dynamically typed. In production PySpark, I prefer DataFrames for readability, performance, SQL compatibility, and optimizer support. Make sure to cover abstraction levels, schema awareness, optimization through Catalyst, type safety differences, Python limitations around dataset, performance implications, and why DataFrames are usually preferred in PySpark. Question 3. What is lazy evaluation in PySpark, and why is it useful? Lazy evaluation means Spark does not execute transformations immediately. Operations like filter, select, and join build a logical plan, while actions like count, show, collect, or write trigger execution. This helps Spark optimize the full pipeline before running it, for example by pushing filters earlier or combining stages. It also avoids wasted work if intermediate results are never needed. I always remember that debugging requires an action to materialize results. In your answer, talk about transformations versus actions, logical and physical plans, optimization before execution, lineage construction, reduced unnecessary computation, and common actions that trigger Spark jobs. Question 4. What happens internally when you run an action like count on a DataFrame? When count is called, Spark converts the DataFrame lineage into a physical execution plan. The driver creates a job, splits it into stages based on shuffle boundaries, and launches tasks across executors. Each task counts records in its partition, then partial counts are aggregated back to the driver. If the plan includes filters, Spark can optimize them before scanning. The important point is that the driver coordinates, executors do the distributed work. Be sure to mention job creation, DAG construction, stages, tasks, executors, partition-level execution, shuffles if needed, driver coordination, and how results are aggregated back. Question 5. How do transformations and actions differ in PySpark? Give examples. Transformations create a new data frame or RDD, but do not execute immediately. Examples are select, filter, with column, group by, and join. Actions trigger computation and return results or write data, such as count, collect, show, take, and save. In practice, I build my pipeline using transformations, then trigger it with a write or validation action. This distinction matters because performance issues appear only when an action actually launches Spark jobs. While answering, define both categories, give practical examples, explain lazy behavior, identify job-triggering operations, and mention why understanding this distinction helps with debugging and performance tuning. Question 6. What is a shuffle in Spark, and why is it expensive? A shuffle is Spark's process of redistributing data across executors, usually by key. It happens during joins, group by, distinct, repartition, and some aggregations. Shuffles are expensive because data moves over the network, may spill to disk, and often requires sorting and serialization. They also expose data skew problems. I reduce shuffle cost by filtering early, selecting required columns, using broadcast joins, salting skewed keys, and choosing partition counts carefully. Make sure to cover data movement across partitions, network and disk I/O, operations causing shuffles, sort and serialization overhead, skew risk, and techniques to reduce unnecessary shuffling. Question 7. How would you optimize a slow PySpark job? I start with the Spark UI, not guesswork. I inspect slow stages, shuffle read and write, spill, task skew, and executor utilization. Then I check the query plan with explain, remove unnecessary columns, push filters early, and use efficient formats like Parquet. For joins, I consider broadcast or repartitioning. If Python UDFs are present, I replace them with built-in functions where possible. Optimization is iterative. Measure, change one thing, measure again. In your answer, discuss Spark UI analysis, stage and task metrics, shuffle size, skew, partitioning, caching, broadcast joins, predicate pushdown, file formats, executor sizing, and avoiding Python UDFs. Question 8. What is data skew in Spark, and how do you handle it? Data skew happens when some partitions get much more data than others, often because one key is extremely common. In the Spark UI, it appears as a few tasks running much longer than the rest. I handle it by filtering or separately processing hotkeys, using salting for joins or aggregations, enabling adaptive query execution, or broadcasting small tables. The best fix depends on the data pattern, so I validate key distribution before changing logic. Be sure to mention uneven key distribution, long-running tasks, identifying skew in Spark UI, salting, broadcast joins, adaptive query execution, repartitioning, and business-aware key handling. Question 9. Explain broadcast joins in PySpark. When should you use them? A broadcast join sends a small data frame to every executor, so Spark can join locally with a larger data frame. This avoids shuffling the large table, which can be a major performance win for dimension lookups. I use it when one side is small enough to fit in executor memory. Spark can choose it automatically using the broadcast threshold, or I can hint it with broadcast. The risk is executor memory pressure if the table is larger than expected. While answering, focus on avoiding shuffle, broadcasting small dimension tables, memory constraints, auto broadcast threshold, explicit broadcast hints, join strategy inspection, and risks with unexpectedly large datasets. Question 10. What is the difference between repartition and coalesce in PySpark? Repartition creates a new partition layout using a full shuffle, so it can increase or decrease partitions and balance data better. Coalesce usually reduces partitions without a full shuffle, making it cheaper but potentially less balanced. I use repartition when I need even distribution, especially before joins or wide processing. I use coalesce to reduce small output files after heavy filtering. The trade-off is cost versus data balance. Make sure to explain partition count changes, full shuffle versus narrow dependency, increasing versus reducing partitions, output file control, performance trade-offs, and common use before writes. Question 11. How does caching or persisting work in PySpark, and when is it useful? Caching stores a DataFrame's computed partitions, so Spark does not recompute its lineage every time it is reused. It is useful when the same intermediate dataset feeds multiple actions or branches. Cache is lazy, so it materializes only after an action. Persist lets me choose storage levels like memory, disk, or serialized formats. I avoid caching blindly because it consumes executor memory and can evict useful data. I unpersist when the dataset is no longer needed. In your answer, talk about repeated DataFrame reuse, lazy cache materialization, storage levels, memory and disk trade-offs, unpersisting, and why caching everything can hurt performance. Question 12. What are the common causes of out-of-memory errors in PySpark jobs? Common causes include calling collect on large data, broadcasting a table that is not actually small, skewed partitions, too few partitions, excessive caching, and memory-heavy Python UDFs. Executor memory can also fail due to shuffle spill or large aggregation states. I fix this by processing data distributedly, increasing partitions where appropriate, reducing columns early, handling skew, tuning memory overhead, and avoiding driver-side operations. The driver should receive summaries, not raw big data. Be sure to cover collect misuse, large broadcasts, skewed partitions, oversized executor memory pressure, bad partitioning, cache overuse, Python worker memory, and strategies for safer processing. Question 13. How do you handle nulls and bad records in PySpark pipelines? I handle nulls based on business meaning, not just technically. For required fields, I validate and reject or quarantine bad rows. For optional fields, I may use fill-na, coalesce, or conditional logic. While reading files, I use modes like permissive, drop malformed, or fail fast, depending on quality requirements. I also track bad record counts and reasons. In production, silently dropping data is dangerous, so I prefer auditable error handling. While answering, discuss schema validation, null handling functions, drop versus fill decisions, malformed input modes, data quality checks, quarantine tables, and preserving auditability. Question 14. What is the Catalyst optimizer in Spark? Catalyst is Spark SQL's query optimizer. When I write DataFrame or SQL code, Spark builds an unresolved logical plan, resolves columns and types, applies optimization rules, and produces a physical plan. It can push filters, prune columns, simplify expressions, and choose join strategies. This is why DataFrames usually outperform handwritten RDD logic. The practical habit is to use built-in functions so Catalyst can understand and optimize the work. Make sure to mention logical plans, rule-based and cost-based optimization, predicate pushdown, column pruning, join reordering, physical plan generation, and why DataFrames outperform low-level APIs. Question 15. Why are Python UDFs often slower in PySpark, and what alternatives do you prefer? Python UDFs are slower because data must move between the JVM and Python worker, often row by row, and Spark cannot fully optimize the custom logic. Catalyst sees the UDF as a black box. I first tried built-in PySpark functions, SQL expressions, or higher-order functions because they run in Spark's optimized engine. If custom Python logic is unavoidable, I consider Pandas UDFs with arrow for vectorized execution, but I still measure the impact. In your answer, cover JVM Python serialization, row-wise execution overhead, Catalyst optimization loss, built-in functions, SQL expressions, higher-order functions, Pandas UDFs, and arrow benefits. Question 16. How would you read and write data efficiently in PySpark? For efficient I/O, I prefer columnar formats like Parquet or ORC with compression, because Spark can read only needed columns and push filters down. I define schemas explicitly instead of relying on expensive inference. While writing, I choose partition columns based on query patterns, not high cardinality fields. I also control output file sizes to avoid small file problems. Good storage layout often improves performance more than adding cluster resources. Be sure to discuss columnar formats, compression, partition pruning, schema inference versus explicit schema, predicate pushdown, small files, write modes, and layout decisions for downstream queries. Question 17. What is partition pruning, and how does it improve performance? Partition pruning means Spark skips reading entire folders or partitions that cannot match a filter. For example, if data is partitioned by date, and I query one day, Spark reads only that date's files. This reduces scan time, network I/O, and cost. It works best when filters use partition columns directly. The trade-off is choosing partition columns carefully. Too many high cardinality partitions create small files and metadata overhead. While answering, explain directory-based partitioning, filter conditions on partition columns, reduced file scanning, proper partition column selection, pitfalls with high cardinality, and relation to data lake design. Question 18. How do you use window functions in PySpark? Give a practical example. Window functions calculate values across related rows without collapsing them like group by does. I define a window with partition by and order by, then apply functions such as row number, rank, lag, lead, or sum. A common example is deduplication, partition by customer ID, order by updated at descending, and keep row number equal to 1. They are powerful for analytics, but they can be expensive because partitioning and ordering often trigger shuffles and sorts. Make sure to cover partition by, order by, window frames, ranking and analytical functions, running totals, deduplication use cases, and performance impact from sorting and shuffling. Question 19. How would you design an incremental ETL pipeline using PySpark? I design incremental ETL around a reliable change indicator, such as updated at, ingestion timestamp, or CDC sequence. Each run reads only new or changed partitions, transforms them, validates counts and quality, then writes idempotently using overwrite by partition or merge when supported. I store checkpoints or audit metadata so failed runs can restart safely. I also plan for late arriving data by reprocessing a lookback window. Reliability matters more than just speed. In your answer, discuss watermark or checkpoint columns, idempotent processing, partitioned reads, merge upsert strategy, schema evolution, late arriving data, validation checks, and recovery from failed runs. Question 20. What Spark UI metrics do you check when debugging a PySpark production job? I use Spark UI to find the bottleneck before tuning. In the SQL tab, I inspect the physical plan and expensive operators. In stages, I compare task duration, shuffle read and write, spill, and input size to detect skew or heavy shuffles. The Executors tab shows memory, GC time, failed tasks, and utilization. The Storage tab confirms whether cached data is actually materialized. These metrics turn performance tuning from guesswork into evidence-based debugging. Be sure to mention jobs, stages, tasks, Executor tab, Storage tab, SQL tab, shuffle read write, spill, skewed task duration, GC time, failed tasks, and query plans. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.